Okay, so let's discuss a bit about basis and dimension. Let's say okay. Basis and dimensions. Basis and dimension of a vector space. Okay. So as we all know that if you have a non-empty set V, okay, and you have an additive binary operation with V such that it's an abelian group. Okay, so number one, so you have for all V1, V2 and V1 plus V2 is also in V. For all V1, V2, V3 in V, you have V1 plus V2 plus V3 is equals to V1 plus V2 plus V3. Number 3, let's say you have for all V in capital V, there exists an element 0 in V such that V plus 0 is equals to 0 plus V is equals to V. Number 4, for all V in V, there exists a unique minus V in V such that V plus minus V is same as minus V plus V, and this is equals to 0. Okay. And number 5, for all V1, V2, V, V1 plus V2 is same as V2 plus V, right? So if these first four axioms hold, then we say V with respect to plus. So this is an additive group. This is an additive group. And the fifth point says that V is an additive abelian group. Is an additive abelian. Okay, one second. Yeah, fine. Okay. So this is a simple extension of. I think these things have been studied in group theory, right? Okay. So if V is an additive abelian group, V is so let V plus be an additive abelian group. Be an additive abelian group. Let F be a field. Let F be a field such that a certain scalar multiplication is defined. That is, for all C in F, CV is in capital V for all V in capital V. So this is called the scalar multiplication. Okay. Now, with respect to scalar multiplication, certain axioms need to be followed. That is, for all C1, C2 in F, C1 plus C2V is equals to C1V plus C2V. This happens for all C1, C2 in F, for all small v in capital V. Number two, if you have C1, C2 with V, then you can associate them as C1 times C2V. This also happens for all C1, C2 in F, for all small v in V. Next, you can also distribute with respect to V itself. Okay, so if you have some C times V1 plus V2, then this can be written as CV1 plus CV2. This happens for all C in F, for all V1, V2 in V. And number 4 is that 1 times V is V. Right? 1 is the multiplicative identity of the field. Right? So a field structure is basically defined to be an kind of an a mixture of an additive abelian group and a multiplicative abelian group, right? So it has a multiplicative identity. We often call the multiplicative identity to be an unity. Okay. So the unity is basically symbolized as one, and it behaves as our algebraic one. So these four axioms need to be held, and the first five ones also. In this case, we say V is a vector space. In this case we say V is a vector space over F. Clear? And we define this as, sorry, we denote this as V over. There are majority of examples like C over itself, C over R, C over Q, R over itself, R over Q. Basically, any arbitrary field F and any n tuple field F over the field F itself. So therefore, F on F is already a vector space. So there are many examples of vector spaces. We don't focus much on these examples because that is not the concern of this lecture. So so we need to move towards what is the main concern of this lecture. So let us first discuss what linear dependence means. What is the concept of a linear dependence? Okay. So, so before understanding linear dependence, we need to understand what is the concept of a linear combination. That is a pretty easy thing. So suppose you have some n elements. Okay, let's say v1, v2 till vn. Let us consider them elements to be from a vector space. So let them be from a vector space Vf. Elements in a vector space are called a vector, like very literal. So they are called, so they are vectors, and let C1, C2 till Cn be elements from the field. So elements from the underlying field are called scalars. Okay. Then C1 V1 plus C2 V2 and so on till Cn Vn. So this structure is called a linear combination. Is called a linear combination of elements V1 V2 till Vn with respect to the scalars C1 C2 till Cn. Clear? Okay. So linear dependence is basically, so suppose you have a vector space V. Let V be a vector space. So let V be a vector space over A. Let S be a subset of V, let's say. Okay. So okay, suppose I define first what is the linear independence of a given set of vectors. Okay. So let V1, V2 till Vn be vectors from V. V vectors from V. Okay. Then they are said to be linearly dependent. That is, these vectors are said to be linearly dependent if there exists scalars C1, C2 till Cn, not all zero. Not all zero. This is a fairly important one, that not all these scalars are zero, such that C1 V1 plus C2 V2 and so on till say Cn Vn is equals to 0. Okay. So basically, n some n number of vectors, distinct vectors, obviously, because we are considering sets, right? So n distinct vectors are said to be linearly dependent if there exists scalars, not all zero, such that a linear combination of those vectors with respect to those scalars can equal 0. An ordinary example of this might be, let's say, if you consider this vector space say R2 over R, and if you choose these vectors, let's say, so you have 1 minus 1 and say minus 1 1, then obviously 1 times 1 minus 1 plus 1 times minus 1 1, this equals 0. So both of them are non-zero, right? So this is a very pretty, easy example to just understand what happened. What is basically happening. If you want certainly a different kind of an example, you can think of it like, say, suppose you have 2 minus 1 and you have 1, let's say 1, and suppose 2 minus 2, and here you have 1 minus 1. Then notice that 2 minus 2, that is 1 times 2 minus 2 times 1 minus 1. So minus 2 times 1 plus minus 2 times this equals 0, right? And minus 2 and 1 are from R, obviously. Clear? So this is a linearly dependent set. Certainly, if some elements are not linearly dependent, then they are linearly independent. So not linearly dependent means linearly independent. Linearly independent. So the definition of linearly independent is like, say, so v1, v2 till vn in some vector space V over F is said to be linearly independent if you consider a certain linear combination of them. So say c1 v1 till say cn vn equals to 0, and this happens only if c1 equal to c2 and so on till equal to cn is equals to 0. So all these scalars need to be 0 if the linear combination is 0. Clear? So an example of this is very trivial example we have. Again, we can consider R3 over R, this vector space. So if you choose these elements, let's say 1 0 0 0 1 0 and 0 0 1, so they are linearly independent. Why? Because if you choose a certain linear combination of them, let's say, so suppose you have c1 times 1 0 0 plus c2 times 0 1 0 plus c3 times 0 0 1, this equals 0 means 0 0 0, obviously, because the 0th element of R3 is 0 0 0. So then you can just so the scalar multiplication defined on an n-tuple space is basically component wise scalar multiplication and component wise addition. This basically becomes c1 0 0 plus 0 c2 0 plus 0 0 c3 plus to 0 0 0. So you add them up, this becomes so c1 plus 0 plus 0, so component wise addition. So this is c1, this is c2, and this is c3. And so on either side of the equality, a comparison is again component wise. So this implies c1 equal to c2 equal to c3 must be 0. Therefore this set is linearly independent set. Clear? Now if you consider an arbitrary subset of a vector space, so suppose S is a subset of a vector space V, then S is said to be linearly dependent if some n vectors from F, or I should frame it like this, that so a subset S of a vector space Vf is linearly dependent if any n distinct vectors from S is linearly dependent. Okay. So if you choose any n distinct vectors from S and they come out to be linearly dependent, then we say that the set is linearly dependent. Otherwise it's linearly independent. So And that is the definition we choose for an arbitrary subset. Arbitrary subset in the sense we do not know exactly whether the set is finite or infinite. So that is the thing. Clear? Okay. The next required definition is what is the linear span of certain elements. So let me define it like this. So let's say, suppose let's say V is a vector space. So V is a vector space and S is a subset of V. Okay, S is a subset of V. Then S is said to span V. S is said to span V, or it's termed as S is the spanning set. Or rather, I should not use this definition indirectly. I should first define what a linear span is. Then a linear span of S denoted as LS is defined as the collection of linear combinations, all linear combinations of n distinct elements from S. Clear? Collection of n distinct elements from S. So you can think of it like this. Let's say, so L of S is the set of summation I equals to 1 to n Ci small si such that small si belongs to S. So things are much simpler if S is a finite set. Okay, finite countable set, right? In case of countable sets, it's very easy to think of things like this, right? Because if S is, say, the set of vectors v1, v2 till vn, then the linear combination is obviously of the same form, obvious. Okay, but it's much more intriguing. Right? So it's CIVI, right? So that each vi is from S and each Ci is from the underlying field. Clear? Now we say that S spans V. S spans V, or S is a spanning set. S is a spanning set of V if the linear span of S equals V. If a linear span of S equals V. Okay. Now, since V is closed under addition and scalar multiplication, so obviously the linear span is contained in V, right? Now it's obvious that the linear span of any subset of S, it is contained in V. So it suffices to check whether V is contained in the linear span of S or not. Because if it does, then so we have an either side inclusion, right? So V must equal to LS. Clear? Got it? Okay. So these are the basic definitions we actually require to have a conceptual understanding of what a basis is. Yeah. So now we come up to the definition of what a basis is. So let V over F be a vector space. B is said to be a basis of V if and only if, point number 1, B is linearly independent, and number 2, the linear span of B equals V. That is, B spans V. I should also mention here that B is a subset of V. So a subset of V denoted as B is said to be a basis of V if and only if B is is linearly independent and the linear span of B equals V. Clear? Examples. Example number 1. These are the example which we previously chose. That is this set 1 0 0 0 1 0 0 0 1. Right? So this is a basis for R3 over R. Now, why is it so? Now we have already proved that this is linearly independent. We just need to show whether this spans R3 or not, and that is very easy to check, because suppose if you have X in R3, then that means X has certain coordinates x1, x2, x3, because you can imagine R3 to be the three-dimensional space, right? So it has certain coordinates with respect to the x-axis, y-axis, and z-axis. You can think of it like that. So it has the x1 component with respect to x-axis, x2 component with respect to y-axis, and x3 component with respect to the z-axis. But obviously, we can write this thing as x1 times 1, 0, 0 plus x2 times 0, 1, 0 plus x3 times 0, 0, 1, right? So now this element of any element of this form is in the linear span of this set. Suppose this set we mention as B. So therefore, that implies X is in the linear span of B. So that is the other way of saying R3 is a subset of the linear span of B, and that proves that. If you have fair knowledge in vectors, you should have also studied this in a +2 level. Then you know that any vector X, we write it as xi cap plus yj cap plus zk cap, right? Where I cap is a unit vector in the x direction, so that is actually this 1, 0, 0 vector, because 1, 0, 0 vector is basically the point which has intercept of 1 in the x-axis and zeros in all the other axes. So that's indeed a unit vector in the x direction. 0, 1, 0 actually refers to the unit vector in the y direction, and k cap, that is 0, 0, 1, it actually gives the unit vector in the z direction. Clear? Another important example of a basis, you might say, suppose V is the set of all, or rather I can just mention it like a vector space of all polynomials over R, will do over R with degree less than equal to 2, let's say. Then the set 1x x squared forms a basis over V. Now this is very trivial, because any polynomial you choose from V, that always has a general form of a0 plus a1x plus a2x square. So indeed this is a linear combination of these elements itself. So V is obviously in the linear span of these elements, and this set is linearly independent, because if you consider a linear combination of this, suppose a0 plus a1x plus a2x square, and this u equal to 0, so this should happen for all x in R, right? But that is actually not possible, because a polynomial of degree less than equal to 2 can have at most 2 roots. So it cannot consider roots from whole of R. I mean, all the elements of R cannot be root of it. So that's a contradiction, because it can have at most 2 roots. Therefore, the only possibility is if all the that is this polynomial. This polynomial is itself a zero polynomial. So other way of saying it is that the scalars, I mean the coefficients are all zero. Clear? So now when you know what the basis is, so if V is a vector space over a field R, over a field F, and B is a finite basis of V, then the number of elements in the basis V is the dimension of clear? Number of elements in the basis B is the dimension of V. If the basis is not finite, rather I should add a term here, that and in this case V is said to be finite dimension. So if the basis is not finite, then V is said to be infinite dimension. infinite dimensional. For example, Rn over R, or rather I can say just Fn over F. So this is a finite dimensional vector space, because the basis it has is the set of elements 1, 0, 0, 1, and so on till the last element, the 1. And there are n such elements. So there are n such elements. Clear? An infinite dimensional vector space can be the vector space V. This is the vector space of all polynomials. Over R. So what will the basis of V? The basis of V must be 1, x, x square, x cube, and so on, x to the power n, and it continues. Because we have no definite degree of the polynomial, right? So it can have any arbitrary. Clear? Now, for example, C with respect to C, this is a finite dimensional vector space because its basis is just 1. C over R is also a finite dimensional vector space. Its basis is 1i. But C with respect to Q is an infinite dimensional vector space. It is an infinite dimensional vector space. Clear? Got it? Okay. A few facts about, one thing which should be arising in your mind is that suppose, I have never said that the basis of a vector space is unique, right? So they can have multiple bases. For example, let's say 1, 0, 0, 1. This is called the standard basis of R2. Typically speaking, this example which I considered here, so this basis is called the standard basis of Fn, FB any field. So this is standard basis of R2. Suppose I consider this space, let's say, suppose it's 1, 1, 0, 1. So this is also a linearly independent set. This is also a linearly independent set. So this also forms a basis. This is also a basis of R2. Okay. So we have two different bases. So there can be multiple bases in a vector space. Okay. The existence of a basis is there, but the basis must be unique is not mandatory. They can have multiple bases. Now the question which arises is that can we find a smaller basis? Okay. So can we find a smaller basis? Now the most trivial answer to is that it is basically that if we find a smaller basis, then the definition of dimension of a vector space is no more well defined, right? Because suppose I have a basis which has n elements, so with respect to this, dimension of V becomes n. But if I get a smaller basis, say V dash, which has number of elements, say m, where m is less than n, then with respect to this, we have dimension of V to be m, which is less than n, obviously. So we have two different dimensions of one single vector space, and that is not quite possible. So this can be the most trivial answer, because otherwise there would have been no question of what dimension of a vector space is. Okay. But somewhat we will try to come up with a result to it, that the number of elements in a basis is fixed. Number of elements in a basis is always fixed. That is, if you have a vector space V, then every basis will have the same number of elements. Okay. So to prove that, we need a theorem. Theorem says that if let V be a finite dimensional vector space. Now see, this theorem is obviously related to finite dimensional vector space, because we are readily using the concepts of cardinality, right? And to be very honest, the concepts of cardinality actually relies on finite sets, because if a set is infinite, then actually cardinality has no meaning. So cardinality has a direct meaning to to finite sets, to the number of elements residing in a set, right? So let V be a finite dimensional vector space over a field, let's say F. and let V be spanned by the vectors beta 1, beta 2 till beta n. Then any linearly independent subset of V is finite and cannot contain more elements than n. Clear? So let us come up with a proof of it. Okay, let's see. So let me decrease the size of it. Let's see. So we are given that V is a span of these vectors. Okay, so it's the linear span of the elements alpha 1, so it's the span of the elements beta 1, beta 2, and so on till some beta n, right? Now let S in V be linearly independent and let S be alpha 1, alpha 2 till alpha n, okay, where n is greater than n. Now first thing first, so if V is a finite dimensional vector space, okay, so we are considering a set S which is linearly independent with certain n number of elements where n is arbitrarily greater than m. We have no restriction to n. It's just greater than m. Somehow, if we obviously prove that n must be less than equal to m, then it's already proven that this set must be finite. Yeah, because m. Yeah, I'm using here n, right? So here must be most of m elements. Yeah, m must be greater than m. Okay. Now each alpha j is in V. Therefore, there exist scalars ai. So I ranges from 1 to m, such that each alpha j can be written as summation I is equals to 1 to n. Sorry, ai beta I. Yeah, I ranges from 1 to n, right? So this is n. Ai beta I. Clear? Now, if so, then this linear combination bi bj alpha j, j is from 1 to m, correct? So this is equal to summation j equals to 1 to m ai and sorry, so j equals to 1 to m bj times summation I is equals to 1 to n ai beta I. So these are finite sums, so can be interchanged, right? So we can write it as summation I is equals to 1 to n times summation j is equals to 1 to m. We have bj. Okay, this first thing first, this scalar must be of the form aij, because this scalar is depending on this index j and this index I. So this is aij. So we can write it as summation over I equal to 1 to n, summation over j equal to 1 to m, aij, bj, and outside you have beta I. Okay. Now suppose we consider this to be 0. Okay. Suppose this is 0. Okay. Now if this is 0, then notice that now see this the inside is simply a matrix multiplication, right? This inside is simply a matrix multiplication of a matrix A is equals to aij with a column vector B is equals to bj. But notice j ranges from 1 to m. That is, the column part is m and the row part is n. So it's a n cross m matrix. A is an n cross m matrix, and n is less than n. N is less than n. So basically, this is a case where the number of unknowns is greater than the number of rows, right? The number of unknowns is greater than the number of rows. So a system of linear equations A is equals to 0, this type of a case, because since, so you have, so this is a span, right? This is a span. Now if I consider this to be 0, if I consider this part to be 0, then this is somewhat the case where Ax equals to 0. This sort of a problem it is, right? So there can obviously exist non-zero BJs. There can exist non-zero BJs, because this is somewhat a case of Ax equal to 0 where there are more unknowns than rows. So if there exists non-zero BJs, then that would imply that S is linearly dependent, but that is a contradiction. That is a contradiction, because S was assumed to be linearly independent. So that means the n must be less than equal to, sorry, m must be less than equal to 10. Okay, that is the, so but then obviously then it's finite. So now if I imply this to the fact that, so you can consider this to be a corollary, that dimension of a vector space is unique. Now how do we say so? So the proof is fairly simple. So let V be a vector space. V be a vector space. Let B1 and B2 be two distinct bases of V with n and m elements respectively. Okay, so with n and m elements respectively. Clear? Okay. So now, so B1 is a spanning set. Right? B1 spans. So using the previous theorem, we can obviously say that any linearly independent subset of V must have number of elements less than B1, right? So therefore, if we consider B1 to be a spanning set of V, and since B2 is a linearly independent subset of V because it's also a basis, therefore M must be less than equal to N by the previous theorem. Now, if we interchange the roles of B1 and B2, that is now if we consider B2 to be a spanning set of V, then number of elements in any linearly independent subset of V must be less than equal to B2, less than equal to the number of elements in B2. So if we consider B1 to be the linearly independent subset of V, while B2 is the spanning set, then N must be less than equal to M. And both of these statements basically means that M must be equal to M. So that is all actually what we actually require to prove. Right. So dimension of a vector space is fairly unique if it exists. Okay. Now, there is one more a very simple result, that is, I will better give it as a lemma and won't prove, because proving this is fairly simple. That is, let S be a linearly independent subset of a vector space V. And suppose we choose a vector small v from capital V such that V is not in the linear span of S. If V is not in the linear span of S, then S union V is also linearly independent. So if I give a brief hint to how the proof is basically, now see, so if V is not in the linear span of S, so okay, suppose S union V is linearly dependent. Okay. Then obviously there exist scalars B1, B2 till Bn plus 1 such that not all 0, right? Not all 0. So let S be the elements S1, Sn, let's say. Okay. Or rather, you can keep this arbitrary. You can keep this simply arbitrary. So not all 0, such that b1 s1 and so on till bn sn plus bn plus 1 v, this is equals to 0. So suppose bn plus 1 is non-zero. So if it's non-zero, then we can write v as minus b1 by n plus 1 is 1 and so on till minus bn by bn plus 1 is n. So that implies v is in the linear span of S, but that's a contradiction, right? Why is a contradiction? Because we are told that v is not in the linear span of S. So that typically means that bn plus 1 needs to be 0. But if bn plus 1 is 0, then suppose this is 1, then 1 basically becomes b1 s1 till bn sn equals to 0. Since S is linearly independent, then b1 must be equal to bn and all these coefficients must be 0, and that is obviously again a contradiction. Why? Because we had considered here that not all the scalars b1 till bn plus 1 must be 0, but eventually we have found the answer that all these scalars are 0. So that's indeed a contradiction. Therefore S union V is linearly independent. Yeah. So that's enough discussion on basis and dimensions. One more very important, description, or rather I should say a theorem related to dimension, is that I'm just writing it down. I'm not proving it. I don't have enough time now, so I'm just proving it as a theorem here. So let W1 and W2 be subspaces of a finite dimensional vector space V. Then dimension of W1 plus dimension of W2 is equals to dimension of W1 intersection W2 plus dimension of W1 plus W2. So elements of W1 and W1 plus W2 is basically, pairwise addition of elements. So W1 plus W2 actually considers elements of the form small w1 plus small w2, such that small w1 is from capital W1 and small w2 is from capital W. Yeah, okay. So meet you guys in the next lecture.